This is an introduction to interior point methods. We're going to set up the theory and methods to be able to solve this, and then I'll show you a couple example applications on how to solve nonlinear programming problems with the interior point method. So as an overview, we have nonlinear constrained problems that we want to try to minimize or maximize. We're going to give just a little bit of an introduction on slack variables, and how we reformulate problems so they fit a standard form, and then talk also about this barrier function, this minus mu times natural log of x, and how we convert x greater than or equal to 0 into this form for the interior point method. We'll talk about the Newton-Raphson method for solving these KKT conditions with this barrier problem, and give a summary of the major steps in the interior point algorithm. We'll go over a couple tutorial examples as well. So first of all, we have this nonlinear constrained optimization problem where we're trying to minimize an objective function subject to some nonlinear equality constraints and some simple variable inequality constraints. And so this can be a linear, quadratic, or general nonlinear objective function constraints. Typically this is applied for convex optimization. It does not guarantee global solutions. And if you do have a maximization problem instead, that can become a minimization problem just by multiplying this by a negative. So it can be minimized or maximized. And we also want to convert these general inequalities into a form like this, and we'll do that with slack variables. So first of all, about slack variables, let's say we just have a general nonlinear problem like this, where we have some inequality constraints, maybe some equality constraints. We're going to convert it into this general form just by using slack variables. So we'll take our g of x minus b, and that's greater than or equal to 0. We'll just set this equal to a slack variable, so that we have two equations now, g of x minus b minus s equals 0. And then we also have another one, which is s greater than or equal to 0. And then we also have our h of x equals to 0. And then these become the c of x equals 0. And then we have our x greater than or equal to 0 and s greater than or equal to 0. So we've converted that into this general form like is shown here. So if we have, for example, this problem right here, we can convert this into an equivalent problem with slack variables. So I'm just going to say that's f of x. That objective function doesn't change. And then we have our product of x1, x2, x3, and x4 minus 25 minus the slack variable equals 0. And then we have the summation of the squares between 1 and 4 minus 40 equals 0, and then our slack variable is going to be greater than or equal to 0. So these are my constraints, c of x. And then I have a simple inequality constraint. So I've formed that in this the standard form that we'll need for the interior point method. Let me just visit this link down here at the bottom. You'll see this this link. If you visit that, then it'll take you to a page on additional slack variables, and you can set up and solve, for example, some slack variable problems here that will show you with this online interface how to solve them. Now I want to talk about the barrier function. So once we have it in this form right here, so let me go ahead and write on this. So we have it in our standard form right here. We're going to convert it into a use a barrier function. So get rid of basically this inequality constraint right here. So we still have our c of x equals 0, but we've translated this into a barrier term. And then we have this mu parameter. As we adjust this mu parameter, as it gets smaller and smaller, this is going to go from the mu equals 10 to mu equals 0.1, and there's this barrier right here. Okay, so it's not, as it's finding the optimal solution, it says that there's a very steep increase right here at the boundary, and so it's going to naturally push it away. So we've essentially translated this inequality constraint into an objective function term. Okay, so we want to only search in the interior feasible space. So we're not going to, that's why it's called an interior point method. It's always going to stay feasible. Okay, so let's just look at an example problem. This is very simple. X minus 3 squared, x greater than 0. Okay, so as we have our mu equals to 10 and we decrease that, like mu equals 1, it's going to get closer and closer to this optimal solution, which is equal to 3. Okay, so our constraint was over here at 0. We weren't on the constraint, but we translated this into with a barrier term there. Okay, so let's do something else now. Now the optimal solution, the unconstrained, is over here at -1, but we have this barrier again right here at a value of 0. And now as it searches, it adds this term here. Okay, this is mu equals 10, and as I decrease it, as I iterate, then my optimal solution is going to get closer and closer to this constraint. Okay, and then at the solution of the interior point method, mu is going to be very small but positive. Okay, and then we're going to basically be at this constraint of 0. Okay, so right here. All right, so that's how we, that's a second example of just translating this simple inequality constraint into this barrier term. Now we don't actually solve it this way in practice. Okay, this is very nonlinear. I'm going to show a way to transform this into a different form. Okay, so we're going to solve the Kirsch-Kuhn-Tucker condition. So we're going to take this barrier problem right here, and we want to find where the derivative with respect to x is going to be equal to 0. So we're going to take the derivative, but we notice we have this this 1 over x term right here. What we'll do is we'll just define z equals 1 over x, and then rewrite our Kirsch-Kuhn-Tucker conditions. Okay, this is where the gradient equals 0. This is where our original c of x equals 0. And then this final one right here is just because we redefined this z value right here, and E is just a column of 1s. Okay, so it just makes the matrix algebra work. It's essentially this equation if you have a lot of x's and a lot of z values. Okay, and actually this should be, I think this should be mu right here. Okay. Yes. Okay, so there, we're going to move on to the next one now. So now what we're going to do is just solve this with Newton-Raphson method. We're going to then use this would be a Newton step. We want to find a search direction for our next iteration. So these are the delta values for x, lambda, or Lagrange multipliers, and then our z values as well. And this wk, okay, that's defined like this. It's just the second derivative, or the second gradient of the Lagrangian. Okay, and so that includes all of these terms right here. We're going to differentiate it twice with respect to x. And then z, capital Z, and capital X are just the diagonals of those x and z matrices. Okay, we're just going to put those right there. Okay, so the nice thing is that we can also rearrange this problem. Okay, just with a little bit of manipulation, we can rearrange it here so that this becomes a symmetric matrix, which is really nice because then we can use a linear symmetric solver that can solve our AX equals B solutions, where A is now a symmetric matrix. Okay, so this is our A matrix right here, and that's our b, and that's like our x. Okay, just ax equals b. Solver, a linear solver. Typically these are large scale and sparse solvers. Okay, like Paradiso, you have MUMPS, you have the Harwell subroutine libraries, and others that can solve these very efficiently. Okay, so then the next thing is, once we found our search direction, we need to find an appropriate step size. So alpha equals 1, that'd be a full Newton step. Okay, but sometimes things like nonlinearities, it doesn't fit that quadratic form that we approximated, we have to cut back. Okay, so we'll try 1, but then we might move down to 0.5 or to 0.25, take a quarter step, for example. And so we're going to use this line search with this step size right here. So we'll scale back, finding our new points. If this equals 1, we'll take a full Newton step with these deltas that we calculated from the search direction. Okay, so two popular approaches to determine alpha. One is decrease in a merit function. Another one is a filter method. Okay, so both of those are possible methods. Decrease in the merit function, we just combine the objective function and then some scalar times the absolute value of our constraint violation, and so that determines if it's a better step or not. Okay, filter methods are going to use a combination of the objective function and the constraint violation, and there's some rules that go in there about accepting a new step size. Okay, convergence criteria, we basically just want to go back to our 3 KKT conditions, and if those are all less than a certain tolerance, then we say we're done. Okay, so we've satisfied the KKT conditions. Okay, so here's an overview of the interior point method. We really want to just obtain x naught, our first our feasible, within the bounds guess value, and then from that we can initialize lambda, our Lagrange multipliers, by solving this set of linear equations. We can also initialize our z naught values with this equation as well. Okay, so those are going to go right here and right there. Okay, so once we have an initial guess, then what we're going to do is now we're going to see if, just go ahead and check for convergence. And if we're less than a certain tolerance, we'll say, okay, we're done. We didn't need to do anything. But if not, then we're going to go down here and compute a search direction. Okay, and that was this formula right here. Don't forget the d value there. And then we have a backtracking line search. So alpha, start off with 1, maybe go to 0.5. You might decrease that with the merit function or a filter method. Okay, so this is a big picture overview. Okay, so we have an example here. There's some more examples on the website of how to do this with some source code. This one will be in MATLAB. And there's some IPOPT code there. The barrier optimizer, similar to the IPOPT algorithm. So here's, for example, this example 4, and you can see that it's going to start tracking in. The minimum is going to be here. I'm going to track in, and then it's going to go right to this point where the optimal solution is. Okay, is this you can see this mu value decreasing right there. Okay, and here's mu equals 2, mu equals 1, 0, and -2. Okay, so near the optimal solution, that's going to be, or the very low mu value, that's going to be the optimal solution. Okay, so let me go back here. A couple different solvers that can solve nonlinear programming problems. The ones that we develop here are the APOPT and BPOPT solvers. Very competitive in terms of percentage solve versus how fast we solve them. This is a standard benchmark plot. This is about 500 problems. So we're working right now to combine APOPT and BPOPT solvers into a single solver that can perhaps beat the performance of some of the other solvers that are out there. Okay, so there's an ample interface. There's also an APMonitor interface as well to this these solvers. I showed one earlier. IPOPT is one of the popular interior point solvers, so I recommend going to check that out. Just go to this website right there. Okay, so you're going to have a couple homework problems on this. One is to use interior point methods to solve this problem. And another one is this problem. Okay, so here's another minimization problem. You know, just two variable problems. You can plot them and show the objective function. There's also a couple online links here you can go to solve these problems through a web interface and look at these headings here. You want to look at these headings right here for the interior point optimizer. This is the IPOPT solver, and here's a little bit of help on what those headings mean. You know, you got the iteration count. There's your objective function, infeasible primal problem, and dual problem. Those are the infeasibilities, a summation of those. This is the log 10 of the barrier parameter, and that's our mu value. D, this is the infinity norm max at the primal step. This is any regularization right here, meaning the second derivative was not positive definite, and so we had to add some values to the diagonal to make it positive definite. And then we have an alpha dual and alpha primal. Those are step sizes for the dual and primal problems, and then you have a line search steps. Okay, so those, if you go back here, you'll see each of those right here, and those are description as it iterates. Okay, you're going to see this printout on what the solver is thinking about, what it's doing. Okay, and there's you want to check for optimal solution found. You can see some stats here in terms of the objective, dual, infeasibility, constraint violation, complementarity, etc. Okay, so homework help for this. You know, I mentioned there is a MATLAB version of it. I'll go to that web page in just a second, and this is, for example, how you solve one of the problems. Okay, and so let me go to that really briefly and just share with you, you know, what we're looking at with that homework problem. Again, just go ahead and use the MATLAB. Okay, so I'm going to. Okay, so go to the website. If you come to the APMonitor.com web page, and then go to take a course. And this will be under the optimization techniques, ME 575. And so it's right here. You can go down to, scroll down on the right, and you're going to see the interior point method. So go ahead and select that, and then it has these lecture notes along with all of the examples, and also a video that shows you how to do one of the homework solutions. Okay, and a little bit more help there as well. And some of these example problems. Okay, so this is some material on interior point methods as part of the optimization course.